Welcome to video lecture for VLSI design. We are looking at unit 4, that is floor planning and placement. So I hope you have watched lecture 1, 2 and 3. The objective of this video is to make you to explore the associated details like interconnect routing techniques and wire parasitics. First we'll look at interconnect routing techniques. So what happens when we route the power supply or when we route the chip, and when we are interconnecting them, how to do this is what is called as interconnect routing techniques. Chip level wiring design is usually divided into two phases. They are global routing, which assigns wires to routing channels between the blocks. What are these wires? These wires are nothing but the metal lines which are supposed to pass the clock or else the power supply. They are generally called as power lines and clock lines. So they are passed through metal lines. So instead of that, here we are going to call them as wires. Detailed routing is the other technique, other phase. It designs the layouts for the wiring. What is global routing? Let's see. We are supposed to see the routing algorithms, global routing utilization as a metric, and in the global routing we are going to see line probe routing. So the line probe routing is the one which passes the signal or passes the wire in the form of lines. So in this particular diagram you can see the rectangular boxes which are placed in the chip or on the floor are the blocks where we are supposed to place our design, and in between them, for that we need some clock or the supply. They are passed through the lines. So line 1 and line 2, through these lines the routing or the wiring will be done. Next is the switchbox routing. So in the line probe routing, there we can use many routing algorithms, not just only line probe routing. There are so many routing algorithms which are available for global. See, it is not that local, like this to this and this to this and this block to this block. It is not so. It is globally, and from this lines globally we are supposed to tap, and then we are supposed to make use of this supply or the block. So utilization is little difficult in the global routing. Next is the switchbox routing. A switchbox may be used to route wires between intersecting channels. The track assignments at the ends of the channel define the pins of the switchbox. It is often possible to define channels without requiring switchboxes, but switchboxes may sometimes be necessary in floor planning. So a switchbox formed at the intersection of two channels, you can see. So this is one channel and this is the other channel. So here comes the interconnection of these two called as a switchbox. So this switchbox may now be used to route the wires between the intersecting channels. So this is the routing line, you can see here. This is the routing line. This is used to connect them. So these track assignments define the pins of the switchbox. There happens that when we route, some glitches and glitches in the power can happen. So like if I pass a signal of this fashion to this NAND gate and one more signal of this fashion to this NAND gate, and directly this form of signal to this NOR gate, then the output of this NAND gate, you can see it is constant and rising and constant. Actually, it is supposed to be the landing of these two, high and high, land is low, low and low, land is high. So low and then high. That should happen. But now, again this low and high, what is NOR? Low and high. NOR of low and high is low. Again, here you can see the falling. The falling and low NOR is this one. So you can see the glitching is a simple network. Glitch is sudden rise or sudden fall or some changes. So this also can happen in the power. So power is nothing but on and off or supply 1 and 0. So when these power supply lines, if they are not constant all the time, if they are changing, then within a logic network when we pass, it shows like a glitch. It is not just low and high. So there is a small change which happens. It is called as a glitch. What are the sources of glitches? Some sources of glitches are more systematic and easier to eliminate. So glitching in a chain of adders, you can see here. So this is a chain of adders. This is a long chain. This is the balanced tree. This is again a chain of adders, but this is not a long chain. This is balanced tree. So here you can see A and B are given to adder, which adds and produces A and B as the output. This A and B again along with the C is given to adder. So now output of this will be A plus B plus C, and again D is given and added, and so output should be A plus B plus C plus D. Getting? But here, if the glitch or sudden fall or sudden rise or some abrupt happens anywhere here or here, if suppose it happens so, then it may produce me only C plus D, or it may produce me only D, or it may produce me A plus B plus C plus D if there is no glitch. Coming to the balanced tree, A and B are, so to avoid such glitches in the long chains, we go for a balanced tree network so that this adder will add A and B and produce A plus B. There is the other adder which adds C and D and produce me C plus D, and these two are given to a adder to produce A plus B plus C. So in this balanced tree structure of adders, there will be a removal of glitch, or we can say there is no occurrence of glitch. So this systematic arrangement will be easy and will eliminate the sources of glitches. What are the signal probabilities? We need to be able to estimate the signal probabilities in the network. The signal probability PS is the probability that signal S is 1. The probability of a transition, that is rise time or fall time PTR, for S can be derived from the signal probability, assuming that the signal's values on clock cycles are independent. So the transition TR, PTR, probability of transition is denoted by PTR for a signal comma S is equals 2PS into 1 minus PS. Now delay independent and delay dependent power estimation. There are two major ways to compute signal probabilities and power consumption. One is delay dependent and the other is delay independent and delay dependent. Analysis based on delay independent signal probabilities is less accurate. It is less accurate than delay dependent analysis, because we need to consider delay and we need to do the analysis. If we don't consider the delay, that means we are not accurate and we may come up with the undefined solutions. So analysis based on delay independent signal probabilities is less accurate than delay dependent analysis, but delay independent values can be computed much more quickly. obviously, because we are not considering any delay, so we can compute it much faster. The time or accuracy trade-offs for power estimation track those for delay estimation is the first one, circuit level methods are the most accurate and costly. Switch level simulation is somewhat less accurate but more efficient. And the third is logic based simulation is less powerful but can handle larger networks. So now moving on to wire parasitic. Wires, vias and transistors all introduce parasitic elements into our circuits. So parasitic components are resistance and capacitance, diffusion wire capacitance, bottom wall capacitance which depends on the diffusion area, side wall capacitance depends on the perimeter. So you can see here side wall and bottom wall. Side wall capacitances here and the bottom wall capacitances, and the depletion region what we have here, there also will be a capacitances. So these capacitances and resistances will now introduce the wire parasitics. So the depletion region capacitance value is given by Cj0 equals epsilon Si by Xd, where epsilon Si is permittivity of silicon and Xd is the depletion region width. And built-in voltage VBI is given as Kt by Q natural logarithm NaNd by Ni square, where XDO is 1 upon Na plus 1 upon Nd into 2 epsilon VBI by Q. This is the junction capacitance you can see here. CJVR is CGO, what is shown here, depletion capacitance at 0 bias by under root of 1 plus VR by VBI. So junction capacitance, this one, decreases as reverse voltage VR increases. As VR increases, the junction capacitance will decrease. Now what are plate and fringe capacitances of parallel plate capacitor? Capacitance formed due to poly and metal wires. Plate capacitance is per unit area assumes infinite parallel plates. And the fringe capacitance is due to changes in the electrical fields at the edges of the plate. You can see here. This is the metal plate. So plate capacitance is on the metal plate, but at the edges here, the capacitance you can see here like change what is shown in a rough structure. So that is called the fringe capacitance, because the electric field at the edges may vary, which leads to a fringe capacitance. Number of metal layers increases and the capacitance of the substrate decrease. The wire-to-wire capacitance or CM1 M2 capacitance between two different metal layers, that is M1 is the metal layer, M2 is the other metal layer. So two metal layers capacitance depends on the area of overlap between two wires. See W1, W2, two different wires. One is W1, wire 1 is W1, wire 2 is W2. So this capacitance is between two wires on same layer. You can see here. So see W1, W2 capacitance between the two wires, 1 and 2 wires on the same layer. This is for both the metal 1. But between metal 1 and metal 2, this is the CM1, M1, M2. That is the capacitance between the two metal lines. At the capacitance between the same metal line but two different wires. This is one wire and this is another wire. So these capacitances will lead to a capacitive coupling between signals on the same and different layers. Now what is the resistance per unit square, which is constant? Wire resistance, the resistance of the wire, here you can see, suppose this is one wire, its resistance is this one. This is another wire, its resistance is this one. Wire resistance are computed by measuring size of the wire. This is unit per unit ohm per square. So this can be again equivalent, like we all know, parallel series resistances. We can make it to a equivalent resistor. But again the resistance is nothing but unit ohm per square. So these are some of the wire parasitics, and in detail again some of the parameters we'll be looking in the next video, next lecture. Thank you for watching.